Hello everyone and welcome to today's webinar, Choosing the Right Adsorbent for Your Thermal Desorption Gas Chromatography Applications. I'm Ed Rakowski, Editor-in-Chief of The Synergist, the magazine of the American Industrial Hygiene Association. I'd like to thank all listeners for attending today's event, and especially our sponsor, the Supelco division of Sigma-Aldrich. The Supelco division researches, manufactures, and supplies chromatography columns and related tools for environmental, government, food and beverage, pharmaceutical, biotechnology, medical, and chemical laboratories. It specializes in 4 main product areas: glass chromatography packings, columns, and accessories, liquid chromatography packings, columns, and accessories, sample preparation products, and chemical reference standards and reagents. Our presenter today, Jamie Brown, is an R&D scientist with the Supelco division of Sigma-Aldrich. He has over 28 years of experience in developing products for sampling organic volatile compounds from air and water. Jamie has routinely assisted regulatory agencies like EPA, OSHA, and NIOSH with method development, and he is an active member of the ASTM D22.05 Air Quality Committee. He has collaborated on methods for domestic and international regulatory agencies through Supelco division's global network of subsidiaries and research partners. And I'll turn the presentation over to Jamie.
Thanks, Regina, Ed. We appreciate all your help today. Hey, we appreciate all of you for taking the time out of your busy schedule to attend our webinar today. Our goal is to provide you with some useful information about choosing the right adsorbents and sampling conditions for your thermal desorption applications. So today we'll cover a brief overview of thermal desorption, an overview of the different types of adsorbents commonly used for thermal desorption, cover some information on sampling conditions, and we'll end with how thermal desorption can be used for industrial hygiene sampling. So what is thermal desorption? It's a sample preparation technique for gas chromatography. The sample is collected onto an adsorbent packed glass or stainless steel tube, and the sample is concentrated on the adsorbent. So this is the tube that's out in the field, either taken an area sample or put on a person to take a personal air sample. After that sample is collected, the tube is taken back to a lab, and that packed tube is heated in a thermal desorber where the compounds are released into the carrier gas, and they're swept to a GC column and analyzed by a gas chromatograph. Today, most thermal desorbers use both a primary sample tube and a refocusing trap. By refocusing the sample, this helps to improve the chromatography of the early eluting compounds. The size of the primary sampling tubes range from 1/4 inch to 6 millimeters and have an internal diameter of 4 or 5 millimeters, whereas the size of the refocusing tube is much smaller with an internal diameter of 1 to 3 millimeters. Thermal desorption can be used to sample most organic compounds. There are a few exceptions, and compounds that are sensitive to thermal degradation, compounds that require derivatization prior to analysis, like formaldehyde and isocyanates, and compounds that are larger than C40 in size. So this slide shows an example of a single bed thermal desorption tube. The tube is made of glass. The adsorbent's held in the heated zone of the tube, and it's held in place by glass wool or a glass frit. It keeps the adsorbent inside. Again, like the inner diameter of a glass tube is typically 4 millimeters, and the OD ranges from 1/4 to 6 millimeters. The overall length of the tube can vary among the different instrument manufacturers. And in some tube designs, the air sample can either be collected actively or passively, and I'll provide some examples later in this webinar. So multi-bed thermal desorption tubes. With a multi-bed, 2, 3, or 4 different adsorbents are packed into the tube. The adsorbents are arranged in an order from weaker to stronger, and this allows us a wider range of compounds that we can sample at the same time. Multi-bed tubes can only be used for active sampling, since the compounds cannot travel through all of the adsorbent beds without the help of an air sampling pump. So tubes are available in both glass and stainless steel. They both have their advantages and disadvantages. The advantages for glass is the glass is most of the time considered more inert. We can see the adsorbents inside, so we can see how the tube ages if everything's still well intact. A glass frit in the inlet keeps the adsorbent in place so it doesn't fall out during sampling. Some of the disadvantages are the tubes can break since they are glass. And if we're using a stainless steel tubes, of course, the obvious advantage is that tube won't break since it's made out of stainless steel. The IDs are typically larger, and this allows a higher sampling flow rate. And some of the stainless steel tubes are also amenable to passive sampling. One disadvantage is you can't see the adsorbent inside. So some of the adsorbent characteristics for an adsorbent to be good for thermal desorption. It must be able to retain and release the compounds of interest. It must be able to withstand high temperatures around 300 degrees C. The adsorbent should have low background levels, low metal content, and should be hydrophobic. Some other desirable characteristics are a constant mesh size, a consistent density, low shrinkage of the particles, and a low amount of fine particles. So this slide shows what happens when we desorb a wide range of VOCs from a strong carbon molecular sieve. Oftentimes we'll get questions is, why can't I just use the strongest adsorbent for everything? The top chromatogram is from a single bed Carbosieve S3, and the bottom chromatogram is from a 3-bed multi-bed tube that also contains a Carbosieve S3, but 2 other weaker adsorbents are placed in front of it. The sample is a gas mix with a 43 compound mix ranging from chloromethane, the lightest compound, to the heaviest being hexachlorobutadiene. Notice that we get good response for the compounds in the early part of the chromatogram from both tubes, but the desorption efficiency is poor for the later eluting peaks desorbed from just the tube with the Carbosieve S3. So what's happening is the larger size compounds are being held too strongly by the pores of the Carbosieve S3, and they don't release during the heating process. This is why we use multi-adsorbents when collecting air samples that contain a wide range of compounds. So now I'll explain some of the terms related to adsorbents. Surface area is a measure of the exposed surface of an adsorbent on the molecular scale. The surface area provides a general idea of the adsorbent strength, but it doesn't provide the whole picture. Other characteristics such as pore size, pore shape, and porosity can also play a role in the adsorbent's ability to retain and release different compounds. As a general rule, the higher the surface area value, the stronger the adsorbent. However, when the surface area is greater than 800 meters squared per gram, the size and shape of the pore becomes more important. Another rule of thumb is adsorbents with surface areas less than 200 meters squared per gram are good at trapping and releasing compounds that are a liquid at room temperature, and those with a surface area greater than 500 meters squared per gram are good to trap and release compounds that are a gas at room temperatures. Pores are classified according to 3 main groups depending on their size. An adsorbent containing the larger macropores are used for the larger semi-volatiles. Those with mesopores are used for volatiles that are liquids at room temperatures, and the small micropores are used for very volatile organics and inorganic molecules that are a gas at room temperature. To complicate things, the molecule of interest also plays a role. Molecules with different shapes and sizes, for example, freon with a large chlorine atom makes the size of this molecule very large. But most freons are a gas at room temperature. But because of their physical size, this allows them to be retained by weaker adsorbents that contain mesopores. So using a multi-bed tube containing different types of adsorbents will always allow us to collect a broader range of compounds than just using a single adsorbent. So now we'll cover some information on the common adsorbents used in thermal desorption. One of the types of adsorbents is called a porous polymer. 10X is the most popular adsorbent used in thermal desorption today. It has a maximum temperature of 350 degrees. It has a recommended desorption temperature of around 300 and conditioning temperature of 320. Methanol is not retained by 10X, so it's very good for spiking our liquid calibration standards made with methanol, because the methanol will travel through the adsorbent and it won't be retained. Some of the other typical characteristics of 10X are it's tan in color, has a surface area of 35 meters squared per gram, and it's hydrophobic. But oftentimes a porous polymer can have a higher background contamination level, making it sometimes hard to reach part per billion detection limits. Some other porous polymers include Porapacks, Chromasorbs, and Aseptes. These have a lower maximum temperature limits of 225 to 290. We desorb them at a much lower temperature, around 200, and a conditioning temperature of 210. Typically, they also have high background levels than other adsorbents and can easily be used for concentrations in the part per million range. The other typical characteristics of porous polymers, they're light yellow in color, surface area ranges from 500 to 800 meters squared per gram, and they're also very hydrophobic. And then we get to the graphitized carbon blacks. They are a pure carbon. They're manufactured at temperatures that exceed 1200 degrees Celsius and exhibit graphite-like properties. Most of the Carbopacks except Carbopack X and Z are non-porous. Since most graphitized carbons don't contain any pores, adsorption takes place by London dispersion forces only, which exist between the molecule and the adsorbent. Carbopack X is one of the strongest graphitized carbons that bridges the gap between other Carbopacks and porous polymers and the stronger carbon molecular sieves. All of the Carbopacks are very hydrophobic, so they're good for sampling high humidity environments. Graphitized carbons typically have fewer impurities than charcoals, making them more inert and useful for trace analysis. This slide shows the rank of the adsorbent strengths of the graphitized carbons. Notice how the stronger adsorbents have more surface area per gram. This slide shows the different retentive strength of the different Carbopacks. What you're looking at is the recovery of 43 compounds from different types of Carbopacks. We packed each adsorbent into its own tube. We then spiked all the tubes with a gas mix containing 43 compounds and then pushed another 200 ml of air through the tubes. And what you see is what was retained by the adsorbent. This mixture contained a range of compounds that ranged in size from chloromethane to hexachlorobutadiene. The top chromatogram in blue shows the response of the gas mix using a multi-bed tube packed with 3 different adsorbents. The next chromatogram in red is Carbopack X. It did a great job of trapping the very volatile compounds, but the recovery of the last 2 compounds is little compared to the others. This is because Carbopack X is too strong for these 2 compounds. As we proceed down, notice how the lighter compounds are not retained, but the larger compounds like xylenes, dichlorobenzenes are well retained. The lighter compounds are simply not being retained by these adsorbents. They pass completely through the adsorbents during the sampling. For comparison, glass beads, the bottom chromatogram, does have some retention of the higher molecular weight compounds, but most of the compounds are not retained at all. So what's the difference between Carbotrap and Carbopack? It's the same material. It's just the size of the adsorbent particles. After they're manufactured, they're placed in a sieving screen to collect the various sizes. The smaller the mesh size number, the larger the particle. Common mesh sizes include like 20-40 mesh, 40-60, 60-80 for thermal desorption applications. So then we move on to the carbomolecular sieves. In most applications, a weaker bed of a porous polymer or a graphitized carbon black should be placed in front of them to keep the heavier compounds from becoming irreversibly absorbed. The only time a carbon molecular sieve should be used by itself is if we're confident that our sample doesn't contain compounds with boiling points greater than benzene. So some of the characteristics of the carbosieves and carboxyls, they have a high maximum temperature limit of 400 degrees, a desorption temperature of 330, and a recommended conditioning temperature of 350. However, methanol is retained on these carbon molecular sieves. Since methanol is also small, they'll be trapped by them. And when we're spiking our calibration standards made with methanol, we have to be careful not to overload during the spiking, so we need to keep those volumes very low. Some of the other characteristics include they're spherical, except Carbosieve G. They're shiny, dull black in color. High surface area range from 400 to 1,500 meters squared per gram, and they're designed to retain and release small molecular weight compounds. This slide ranks the absorbent strength of the carbon molecular sieves, but notice how they aren't in order of surface area now. Now the shape and size of the pores have more influence on the adsorptive strength. This is a general overview of the difference, but it's the size and shape of the molecule we're trying to sample that matters more. Those in blue are the most common carboxyls used for thermal desorption. There are some other adsorbents worth mentioning. Glass beads, as I showed you earlier, perform well in releasing larger molecular weight compounds, so they could be used as a first bed in a multi-bed tube to protect the other adsorbents. They have a high maximum temperature of 500 degrees C. But adsorbents like charcoal don't perform well in thermal desorption because of a variety of reasons. Charcoals are typically not used because they tend to retain the compounds too strongly, and they don't release well used in thermal desorption. Charcoals can also have metal impurities that, when heated, can cause decomposition of the compounds of interest. Silica gel is not used because it's large affinity for water, and it also has a low maximum temperature limit of 190 degrees. Most sieves also have a large affinity for water and aren't very thermal desorption friendly either. So now I'll discuss why adsorbent mesh size is important. An important consideration when packing adsorbent tubes is that relationship of the particle size to the inner diameter of the tube being packed. The best efficiency occurs when the ratio of the particle size to ID of the tube is between 0.1 and 0.25. So the graph, or the picture on the left, shows a tube with large particles in, and during sampling, the compounds can travel around the adsorbent. The picture on the right shows where we've got good packing of the adsorbents. The particles are small enough that the compounds interact with the adsorbent during sampling. So this chart shows the ratio of particle mesh size in different tube inner diameters. So for example, for a 4 millimeter ID tube, the optimal ratio is met with a 2040 mesh particle. A 10 mesh particle is too big, so there's a good chance that channeling will occur during sampling. You can use a smaller mesh size like 6080. This size is smaller than it needs to be. This just results in a higher back pressure of the tube. Oftentimes you'll see 1 millimeter and 2 millimeter ID refocusing tubes packed with 6080 mesh adsorbents, since the inner diameter is typically smaller for these size of tubes. However, sometimes you'll see carbon molecular sieves of the 6080 mesh size packed in a 4 millimeter or a 5 millimeter sampling tube. This is because when the adsorbent is manufactured, it only yields this smaller mesh size. But because a carbon molecular sieve are generally spherical, they exhibit less back pressure, as I'll show in a couple slides coming up. So mesh size and how does it affect back pressure? Compared to other sampling media, thermal desorption tubes usually have a higher back pressure than traditional solvent desorption tubes. Oftentimes, throughout this presentation, you'll hear me mention back pressure or pressure drop. For this presentation, they mean the same thing. So for this experiment, glass tubes were filled with the same volume of each mesh size of Carbotrap B and Carbopack B. Then the back pressure was measured at different flow rates. For example, at 250 mils per minute, the back pressure for a 2040 mesh Carbotrap was 7 inches of water. And then when we moved to a 4060, that back pressure increased to 17 inches of water. When we get to the smaller mesh particles like 6080, the back pressure increased to 42 inches of water. So why is all this important? Most air sampling pumps can only handle 18 to 35 inches of water. So the maximum flow rate we can achieve with a tube packed at different mesh size is, for example, a 2040 mesh Carbotrap, we should be able to get 545 mils per minute. If we go to a 4060 mesh Carbopack, that flow rate would drop to 216 mils per minute. And if we were using a 6080 mesh material, we'd only be able to get 86 mils per minute from the pump because we already reached its capacity. So the shape of the adsorbent also affects back pressure. When a spherical particle like the carbon molecular sieve is packed in a tube, that space between the particle is essentially the same. So the pressure drop will be lower compared to a granular adsorbent because the space varies between the particles, so some of the particles are packed tighter together. This helps explain why the pressure drop can change with tubes packed with granular adsorbents over time. The granular adsorbents will continue packed tighter as the tube is used. Now we'll provide some details on sampling flow rate and sample collection volume. So what's a good sampling flow rate? 50 mils per minute is a good starting point, but there may be times when you need to collect a larger sample volume in a shorter period of time. So using a flow rate of 250 mils per minute may be necessary. Just keep in mind that you could start to lose some collection efficiency if you're sampling above 500 mils per minute. Sampling below 10 mils per minute can cause air to uncontrollably back diffuse into the tube when sampling at very low flow rates. So for recommended sample volumes, if we're using a single bed tube using a hydrophobic adsorbent, anywhere from 1 to 10 liters is a good starting point. And if we're using a multi-bed tube using a carbon molecular sieve, anywhere from 1 to 5 liters of a sample volume is a good starting point. So the most of the time when we're sampling, whether it's people or in the field, humidity is always present at some level. Problems during sampling that humidity can cause is that water vapor can be retained by the adsorbent. The water vapor can mask the available sites of the adsorbents and can, in some cases, display some of the compounds. Problems during analysis include water vapor can alter split flow ratios during desorption, can create chromographic separation issues, and can blow out the FID flame and reduce the vacuum of our MS detectors. We need to keep humidity in mind when sampling, since the quantity of the water vapor can often be in milligrams while the compounds of interest are at nanogram levels. This chart shows the absolute humidity at various temperatures and relative humidity levels. The absolute humidity will tell you how much mass of water is contained in each liter of air sample. For example, if the relative humidity is 60% and the temperature is 25 degrees C, the air contains 14 milligrams of water for every liter of air we collect. So, for example, silica gel is hydrophilic, and that's why we don't use it for thermal desorption, because it'll retain 40% of its own weight in water. Some adsorbents are more hydrophobic than others. 10X, Carbopacks, Carbotraps are very hydrophobic, and virtually no water will be retained in them when sampling in humid conditions. Carbon molecular sieves are still classified as hydrophobic, but at high humidity levels, some water is retained, but that bond made with the water is weak, and it can be driven off at ambient temperatures using a dry purge prior to analysis. So in this experiment, we packed a glass tube with the same volume of each adsorbent, conditioned them all, then subjected them to an atmosphere where the relative humidity was 75% and the absolute humidity was 17 milligrams per liter. This chart illustrates how much water is being retained by the 3 different Carbopacks and 10X compared to a tube packed with silica gel. The solid blue line was the amount of water being collected by the silica gel in the tube. After sampling 2.5 liters of air, the amount of water retained by the adsorbents fluctuated between 0 and 3 milligrams compared to the silica gel tube that collected 43 milligrams of water. So virtually no water is retained during sampling with Carbopacks or 10X. Because there's very little water retained by them, they don't require much of a dry purge prior to desorption. For this experiment, we packed tubes with silica gel, Carbopack B, and different amounts of carboxin 1000. The relative humidity level for these experiments was at 80% and the absolute humidity was 18 milligrams per liter. Solid blue line shows the total mass of water collected by the tube packed with the silica gel. The more carboxin packed in the tube, the more water we retain. Notice after about 5 liters, the amount of water begins to level out. It's nowhere close to the amount retained by the silica gel, so it's still considered hydrophobic. So when designing a multi-bed tube, we try to keep the amount of carbomolecular sieve as small as possible while maximizing the weaker adsorbents such as Carbopack or 10X. This slide shows the relative hydrophobicity of various adsorbents. Carbomolecular sieves will always require a dry purge if used in a humid atmosphere. So what is dry purging? This step typically occurs on the thermal desorber prior to analysis. Dry carrier gas is purged through the tube prior to the tube being heated, and the dry carrier gas will displace the water. But oftentimes you need to figure this out, figure out the correct amount of dry purge you need during your method development. So a dry purge is usually referenced as a volume instead of a time. So the key to dry purging is to allow enough dry gas to pass through the tube and carry the water away, but too much dry purge can actually start to push the compounds of interest through the adsorbent, i.e. breakthrough. So some recommended starting dry purge volumes: 10X and Carbotrap typically only need 1/4 of a liter regardless of the humidity level, and carbosieves and carboxin adsorbents may need 0.5 to 3 liters depending on the absolute humidity level. So some practical ways to determine what dry purge volume is needed kind of offline before we put it on our thermal desorber. Prior to sampling, we'd weigh the adsorbent tube and record its tare weight. After sampling, we'd reweigh the tube. If the difference is greater than 1 milligram, a dry purge is required. So then we'd purge the tube with clean nitrogen or helium at around 50 mils per minute. After a ½ liter had passed through, we'd remove the tube and reweigh it. We'd repeat this every ½ of a liter until the tube weight is within the 1 milligram of its initial tare weight prior to sampling. If it's within 1 milligram, most GC systems can handle this amount of water because we're often splitting some of our sample also. So you would do this offline, and once you figured out how much you'd need, you can program the thermal desorber to do this step for you. So now I'll describe some uses of thermal desorption for industrial hygiene. The picture here shows both a stainless steel and a glass thermal tubes. These tubes shows the tubes sealed before and after sampling. Some advantages of using thermal desorption compared to solvent desorption. A wider range of analytes can be collected on a single tube. Multiple adsorbent beds can be packed in the same tube. Thermal desorption offers more sensitivity than solvent extraction, typically 2 to 3 orders of magnitude since no solvent dilution occurs. Desorption efficiencies are typically 95% if we choose the right adsorbents. No hazardous extraction solvents are required. No solvent interference during analysis. There's a cost savings because the tubes are reusable. Sample prep is automated by the thermal desorber, and both active and passive sampling tubes are available. So NIOSH 2549 is an active sampling method that uses a multi-bed adsorbent tube. Based on its recommended range of flow rates and sample volumes, the sample collection time can range from anywhere between 20 minutes and 10 hours. This tube is useful for screening or for conducting odor complaints. The Carbotrap 349 tube that's specified in the NIOSH 2549 method is packed with 3 different adsorbents. Carbopack Y at the beginning of the inlet, a little bit stronger Carbopack B, and a stronger Carboxyn 1000 that's at the outlet of the tube. So this adsorbent configuration will retain and release a wide range of compounds. So passive samplers don't need an air sampling pump. So there's a couple choices for thermal desorption. The axial sampler on the left is simply an 89 millimeter single bed stainless steel thermal desorption tube with a passive sampling cap and a lapel clip. The radial sampler on the right has an adsorbent cartridge inside the yellow diffusive body. A triangle support plate and lapel clip allows it to be worn by a person. Both types of samplers can be used for both personal monitoring and area sampling. So how does it work? The air sample is collected by the natural movement of the contaminant molecules across a concentration gradient of the air gap of the design of the sampler and the adsorbent inside. So the actual sampler on the left, it has a nominal sampling flow rate of 0.5 mils per minute, and the radial sampler on the right has a nominal sampling rate of 25 mils per minute. So it samples at a much higher sampling rate because of the additional amount of surface area based on its design. The actual sampling rate is independent of each compound, and most manufacturers supply the sampling rate for the compounds that you wish to sample. So this photo shows how the adsorbent cartridge from the Radiello 145 is removed from the sampler and placed into an empty, clean stainless steel thermal desorption tube to be analyzed. So for both active samples and passive samples, the tubes are placed in a thermal desorber. The brass storage caps are replaced with analytical end caps so the thermal desorber can process the tubes for analysis. So here are a few other industrial hygiene methods that use thermal desorption. There's methods from ASTM, ISO, the Health and Safety Executive has methods in the UK. So in conclusions, there are 3 main types of adsorbents used in thermal desorption: porous polymers, graphitized carbon blacks, carbomolecular sieves. There are several factors to consider when choosing an adsorbent: single bed or multi-bed, range of compounds to be sampled, sampling flow rate, sample volume, and dry purge volume. There are several options available for both passive and active sampling. So as another resource for you, we have a report that provides thermal desorption users a tool in choosing the right adsorbent for their application. It demonstrates the relative difference between the most commonly used adsorbents in the field of thermal desorption. It includes adsorption and desorption data on 43 common air pollutants on 24 different adsorbents. We challenge the adsorbents with 6 different sample volumes ranging from 0.2 to 100 liters. The recoveries are displayed in 3 different colors that mimic the colors of a stoplight signal: green, yellow, and red. So I need to acknowledge the trademarks I used in the presentation today. I need to make some acknowledgments, some help here at Sapelco: William Betts, Olga Shamelis, Kristen Schultz, Errol, and the American Industrial Hygiene for hosting this webinar for us. And I'd also like to thank all of you for listening to our webinar today. So Sapelco offers a vast array of thermal desorption tubes designed to fit most thermal desorbers. Feel free to contact us for help in choosing an adsorbent or a pre-packed tube for your applications. Feel free to follow up with questions on thermal desorption or air monitoring in general. You can contact myself or Kristen Schultz, or visit our web page, and we have a complete portfolio of air monitoring products available.
Okay, thanks, Jamie. Just a reminder, looks like we have about 25 minutes for questions. If you'd like to ask a question, please type it into the chat window on the bottom right side of your screen and send to all panelists. Jamie, we have our first question is, how many times can you reuse a thermal desorption tube?
Oh, that's a good question. Typically, we recommend they have a lifetime of about 50 sampling and desorption cycles. If the samples are really, really clean, sometimes we can push that, another 25. And if we're sampling in some very dusty environments, we might only get 25 cycles out of a tube.
Okay. Second question, which manufacturer instruments are your thermal desorption tubes compatible with?
We offer tubes that fit the Perkin-Elmer thermal desorber, the Marks International thermal desorber, Shimatsu. We make tubes that fit Gerstel instrumentation, and we make tubes that fit CDS Dynatherm thermal desorbers.
Okay. Another question, can these adsorbents also be used for solvent desorption?
Yeah, some of these are already in some of the OSHA and NIOSH methods, like the Carbopack and the Carbosieve S3 are in a couple of the solvent desorption tubes. They can be solvently, most of these can be solvently desorbed, especially the carbons. Some of the porous polymers, however, can actually dissolve the polymer in different solvents, so you have to be careful of which solvent you use.
Here's a question from Dan. Please address any shelf life considerations for the sample media.
So the media itself, the adsorbents, really have no shelf life. Once they're packed in the tube, we would then condition that tube so we drive off anything that was collected on the adsorbent during storage. A completed air monitoring packed tube usually ships conditioned. We do sell them also unconditioned, but once they're sealed up in their storage container, they typically have low backgrounds even after a year in storage.
Okay. Here's a question from Vincent. Please address trap selection for the thermal desorber.
Well, a lot of times that refocusing trap has similar adsorbents as our sampling tube, but it doesn't always have to be the exact lineup. Like, for example, you might be sampling with a 3-bed primary sampling tube, and your refocusing tube would have for example, 10x in a carbon molecular sieve in it. And we don't sometimes need as much strength because that transfer volume from during desorption to the refocusing trap is pretty small. We're not challenging the adsorbent very much, and oftentimes we get the advantage of cooling that cold trap, so that helps, in some extent, condense the analytes of interest. So we always kind of try to match it to the tube, but depending on what you're sampling for, if you're not interested in sampling compounds below benzene, you could eliminate or not include a carbon molecular sieve, and that would completely do away with any water problems during desorption, because that refocusing trap won't trap any of the water. So hopefully that's somewhat helpful. Okay.
Another question, will particulate be an interference for analysis?
That can be. If some of these particulates have some organic material on them and we heat them up to 330 degrees, we might off-gas those compounds into the thermal desorber. Over time, if we're, for example, using a glass fritted tube, those particles can, over time, start to block the holes in the glass frit, which would increase the back pressure and cause the tube life to shorten a little bit. Might not be able to, the back pressure would increase too much to use it on an air sampling pump. There are some, another thought that came to my mind. We can add a typical 37 millimeter filter in front of the tube to trap those particles, and you can choose whether to analyze them some other way, but if you want to try to, if it's a very dusty environment, you could put a pre-filter on and just kind of throw away the filter and then just desorb the tube.
Okay. Simon asks, what is the best sorbent for diffusive sampling?
When we get into diffusive sampling, we need, like a carbon molecular sieve is sometimes too strong. So one of the good adsorbents that's working really well for us lately is like the Carbopack X. It's not as strong as the carbon molecular sieve, so it by itself can trap a wide range of compounds compared to some of the porous polymers or the weaker Carbotraps or 10X.
Okay. Richard has a two-part question, so I'll give you the first part. What is the limit on molecular weight / boiling point for using thermal desorption?
Well, that can range from the different instrument manufacturers, but in a sense of the adsorbent, we're looking at around about C40. Some thermal desorbers are designed to process or eliminate cold spots that could possibly recondense the adsorbent or the compounds of interest, like in the valving system. But in the theory of generalized terms, if we can chromographically see them in a GC, we should be able to thermally desorb them also. Okay, and Richard's follow-up question is, can ORBO 42 tube packing be used on a thermal desorption unit? I've honestly never heard of that, so I'd be interested to follow up with Richard to get a little more information on that material, and maybe I could make a recommendation. Okay. Next question. For passive sampling, is there enough surface to allow organic to come in contact with? I'm not sure I got all if I got it, that question came out correctly. For passive sampling, is there enough surface to allow organic to come into contact with? Yeah, I don't understand that. Maybe that person could retype that question for you. Okay. We've come to the end of our questions at the moment. One more just came in. No, that is the same one that I just read to you, Jamie, about passive sampling. So maybe we'll give a couple more minutes here for if there's any other questions from the audience. Jamie, did you have anything, any final thoughts that you wanted to state before we sign off? No, like I said, I'm just grateful that everybody took time out of their busy schedule to join us today, and we hope we were able to give you a few nuggets of information to help choosing, your sampling conditions or choosing an adsorbent in the future. Okay, well, it was a very thorough presentation. My thanks to everyone for attending today. Thanks to Jamie for presenting, and thanks especially to the Sapelco Division of Sigma Aldrich for sponsoring this webinar. Please be on the lookout for notices about other upcoming Synergist webinars, and have a good day.